Okie dokie. So, today we begin our study of electricity. And so the unit begins as what's called electrostatics. So, when we talk about electricity, you think of things such as there's a wall socket, right, where you plug something in, like the hair dryer, and electricity comes out when you plug whatever in. There's your cell phone, which has a battery, or the iPad or whatever, and so that runs on electricity, and it's some mysterious thing that happens inside. You've seen lightning, so that's some form of electricity, and it's kind of all related to what you learned in chemistry, which is when we're talking about the atom. So in the atom, you know that we have a nucleus, and the nucleus has neutrons and protons. So these protons are positively charged, and then surrounding it there are these electrons, and electrons are negatively charged. So when we talk about something becoming charged, gaining charge or losing charge, it's basically the electrons that are moving around. The protons being in the nucleus, the middle of the atom, they're kind of stuck, but a lot of the time electrons are free to move. So we know that like charges repel and opposite charges attract. So in the case of the atom, we have a bunch of positive charge here and a bunch of negative charge, and so we say that the electrons stay there because they are attracted to the middle of the center, the nucleus, the protons in there. It turns out that we'll get to this later. I'll just mention, so charge, we use this variable Q, and what is it? 1.6 times 10 to the negative 19 coulombs. Coulombs, I love that word. That's the charge on an electron. Alright, this is where I was going with that. So the charge on a proton is the same, yet opposite the charge on an electron. And you probably learned that, so they kind of balance out, and an atom would normally be neutral unless it is an ion. So anyway, that we'll get to this later, but the actual amount of charge in terms of numbers. So let's talk about the difference between mass and electric charge, because both of these we say are fundamental quantities. With mass, there's only one type, and it causes gravity. If I can spell it, gravity, and gravity is always attractive. If you're like me, you like your sci-fi, and there's anti-gravity and yada yada, but in terms of our experience and what we've actually seen in this universe, gravity is always attractive. It's caused by mass, and there's only one type of mass. Electric charge, however, comes in two varieties. One we call positive and one we call negative. And this is totally arbitrary. The scientists that were sort of coming up with these conventions could have called one type of charge Joey and the other type Josefina, or could have called them blue and green, but instead we now call them positive and negative charge. So they're the same except they're opposite. And so the electric force can be both attractive and repulsive. I know that sounds bad, but repulsive and attractive. Okay. We also will get into the fact that the electric force is way stronger than the gravitational force, which is weird because you feel gravity every day, like, oh, I'm sitting in the seat, I feel heavy, I've been sitting here forever. Whereas, when you think of electricity, you just think of things happening in wires and you don't really notice it, but we'll talk more about that. The electric force is much stronger than the gravitational force. Okay, so difference between a conductor and an insulator. Let's take a look at this diagram. Alright, or this image. So what we see here is there's a conductor, so there's metal. These look like copper wires. Copper's a good conductor. And then it's surrounded by some insulator. So a wire is a great example of both a conductor and an insulator. And I think you kind of intuitively know what these words mean. An insulator is something that does not conduct, well, actually, because we're using conductor up there, does not let electrons move. Whereas a conductor, we say that electrons move relatively freely. Superconductors, that's a branch of technology on which people are working. If we had superconductors and could transport electricity across the country for free, meaning without any energy loss, that would be amazing. But we don't, because there's some energy loss. So do you know what these are? These are power lines. So anyway, here's New York, or here's the middle of the Yukon, where there's just so much water moving, and we build some dams, let's say, and although the fish wouldn't like it, but we're human, so we don't really care about that. So we build some dams, and it spins these turbines and creates electricity, and then it could go all the way down to San Francisco and power the city, but that is sort of unrealistic just because it's such a far distance. So anyway, electrons are free to move, but not absolutely free to move. So conductor, insulator. Some examples for conductors. We have all the metals and metals. The electrons are kind of free to move. The atoms share. Salt water, so an electrolyte solution. Salt water, electrolyte, or Gatorade. Even just plain water works relatively well as a conductor. This is why you you don't want to make toast in the bathtub. Definitely not. And then an insulator. So air makes a pretty good insulator. Plastic, rubber, glass. So those are examples of kind of typical insulators. We'll see, I know I mentioned lightning up there, but air actually becomes a conductor when there's a huge voltage, and that's what lightning actually is electrons are being ripped out of the air molecules and moved because there's so much electrostatic force on them. So we'll talk about that more later. In our introduction to electrostatics, so by electrostatics we mean we're talking about electrons, we're talking about positive and negative charge, but it doesn't really move. So let me write this. Electrostatics versus electricity, or current electricity. So in electrostatics, the charge remains relatively constant, and one thing that we use to study this or investigate is called an electroscope. So here's my diagram and the one I pulled off the internet. And what we'll be doing is using this, and let's say the PVC pipe works pretty well for collecting charge. So we'll have PVC pipe, and there will be a bunch of negative charges, so an excess of electrons, and we can touch that to the electroscope. So the electroscope is basically a conductor that, so this is a conductor, this is a conductor, there's a glass jar that is insulating, and then these leaves of metal foil. So I think we're going to get to build these, and these will be pieces of aluminum. So they're conductors, and they're kind of free to swing back and forth. So these things can move this way and move this way. So if the electrons reach the conductor, they're free to move in the conductor, and some negative charge will pile up on these things, and therefore they will repel one another. They're free to swing, and so you see this separation here. So a separation of the leaves basically means that charge is present. So charge is present. And by charge we mean an excess of positive or an excess of negative charge. There's all kinds of electrons and protons in here, but in general it's neutral. Okay, so that's an electroscope, and we will, I hope, get to mess around with those in class. Let's take a look at the next page. Oh, wait. Okay. So before we talk about charging by induction, there's a great video that shows this that I'm going to sort of just play for you for that. And we will get to experiment with that in class, but first let's talk about this. So here you see, and you've probably done this, you take a balloon, rub it against your hair or the cat or the carpet or something, and then you stick it to the wall. So here's the wall. And it stays there, and it's magic. How does that work? So what happens is, let's say that you rub the balloon on your hair, and what happens is some of the electrons from your afro are transferred to the balloon. So all of a sudden the balloon has some, it's not just neutral charge, it is now overly negative. So there are more, and I'll draw some positives in there just so we recognize that it's not just electrons on the balloon, but there are more electrons than there are protons. And the wall itself is normally neutral. And what happens if you consider atoms on the microscopic level, the electrons, so here's a not drawn to scale, right? So we got some positive charge, and normally the charge is kind of balanced around it. But what happens is you can have a separation of charge where the negatives kind of move to one side of an atom. So the atom in general has kind of a positive end and a negative end. So we call this separation of charge. Separation of charge. So when we zoom in and we look at the balloon in the wall, what happens is these excess electrons on the balloon tend to pull positive charge towards them and push negative charge away from them. So it's inducing the balloon, and the negative charge in the balloon is inducing a separation of charge. And this is not drawn to scale. It's very slight, but because the electrostatic force is actually very strong, what happens is we have negatives attracting the positives and being repelled by the negatives, but because the negatives are farther away, the attractive force is greater, and that's why the balloon actually sticks to the wall. So the negative charge pulls the positive charge towards it, creating an attractive force that's greater than the repulsive force, and the balloon sticks to the wall. Cool. Alright, so charging by induction. I've got some questions here for you to answer. So this is good. This person describes charging by induction and shows positives and negatives and that kind of thing. So here we go.
Hi folks, I'm going to show you how to inductively charge an electroscope, but in such a way that even when you move the charged object away from the electroscope's terminal, the foils or leaves will still repel each other. You probably already know that if you hold a charged object, like this negatively charged piece of vinyl, near the terminal of an electroscope, the foils or leaves will repel each other. They move apart, like this. And when you move the charged object away, the foils no longer repel each other. They move back together, like this. But to make them repel each other after you move the charged object away, there's just one small step you have to add. Before going into detail on why it works, here's a quick demonstration. All it takes is your finger at the right time and the right place. The key to understanding this is to understand that normally the number of positive and negative charges on the electroscope are equal, and they stay equal. If there's no charged object around, then they're also balanced out everywhere. Wherever there's a positive charge, there's a negative charge to balance it out, or neutralize it. When we move a negatively charged object near the electroscope's terminal, all we're doing is forcing the negative charges away from the terminal and down to the foils. And they'll stay there as long as the charged object is around. When we move the charged object away, the negative charges return to where they were, and everything is balanced out, or neutral again. Everywhere that there's a positive charge, there's a negative charge to neutralize it. But now let's see what happens if I touch the terminal with my finger while the charged object is near the terminal. We start with an equal number of positive and negative charges and everything neutralized. We then move the negatively charged object near the terminal, and many of the negative charges run away to the foils, causing the foils to repel each other. But then, while still holding the charged object near the terminal, I touch the terminal with a finger. As soon as I do that, the foils come together. Then, when I remove my finger, there's no change in the foils. And lastly, when I remove the charged object, the foils repel each other and stay that way. They don't come back together. Let's look at what happened more slowly. When I touched the terminal with my finger, I added another path for the negative charges to take, along my finger and to the rest of my body. This is called grounding. There were still some negative charges on the terminal, but they didn't want to join the other ones on the foil because the negative charges on the foil repelled them. So for them, the repelling force of the negative charges on the charged object was balanced out by the repelling force of the negative charges on the foils. So they stayed put. But with this new path to take, they are repelled to my finger and away. My body's pretty big compared to this electroscope, so I can handle a small negative charge without making a significant difference to my overall charge balance. But now that they're gone, the electroscope's terminal is more positive than it was before, and that attracts some of the negative charges from the foils up to the terminal. Some escape to my finger and some remain. But now the foils no longer have extra negative charges, so the foils no longer repel each other. They come together again. Now with the negatively charged object nearby, we move the finger away. Nothing changes as a result. But now, when we move the charged object away, the foils repel each other. That's because the finger had removed some of the negative charges from the electroscope. There are no longer an even number of positive and negative charges like there were always before when we didn't use a finger. So everywhere on the electroscope there are more positive charges than negative charges. It's no longer neutral. So now the foils are left positively charged. And since like charges repel, the foils repel each other. Another interesting thing is that since the electroscope is positively charged, when we move the negatively charged object close to the terminal, that forces negative charges from the terminal down to the foils, potentially balancing out the positive charges and causing the foils to come together instead of apart. The last interesting thing to show is what happens when I move a positively charged object near the terminal while the electroscope itself is negatively charged, with the foils repelling each other like it is now. Note that when I rubbed the vinyl with the glass, while the vinyl became negatively charged, the glass became positively charged. If I move this positively charged glass near the terminal, that attracts some of the remaining negative charges from the foils up to the terminals, temporarily making the foils even more positively charged and repelling them even further apart. This was all a demonstration of charging an electroscope positively using my finger and a negatively charged object. A similar sequence of events happens if you charge it using a positively charged object instead, and then touch with my finger again. Just keep in mind, the positive charged protons don't move around, only the negatively charged electrons do. In that case, the foils will be left with a negative charge. In summary, this video demonstrated how to charge an electroscope by induction, and in such a way that it stays charged even when we move the charged object away.
Alright, so that was pretty cool. I like how you can actually see the charges, the positives and negatives, and that kind of thing. So, as the dude says, thanks for watching. Yeah.